Welcome back, my friends. We are going to attach to residual Galois representations rho naught from GQ to GL2 of K, where K is a finite field of characteristic P, two more special conditions. And we already attached two conditions to such representations last time. So let's look at those. So last time we took a prime P, at least 3. We took K to be a finite field of characteristic P. We took a Galois representation rho naught from GQ to GL2 of K, and we imposed two simple conditions on it. We wanted rho naught to have mod P cyclotomic determinant, and we wanted rho naught to be semi-stable. We defined what that meant last time. I'm now going to attach a third imposition onto this Galois representation. I want rho naught to be absolutely irreducible. Again, these properties that I'm attaching so far, we're trying to mimic the properties that Galois representations that we're already familiar with have, such as those attached to elliptic curves and those attached to modular forms. Before I get to the fourth condition, I'm going to have to explain what a deformation type is. I'm not going to do that exactly precisely. I'll just give you a naive look at what deformation types are. A deformation type D, it's just a series of conditions that I seek to impose on deformations of a given Galois representation. So I've got this given rho naught. I might look at various deformations rho to different coefficient rings A that have residue field K, and I might seek to require that these rhos, these deformations, have various imposed conditions on them. More precisely, what's going on is a deformation type is a functor from the category of coefficient rings with residue field K to the category of sets. It's given by A mapped to, let's say, D of A, and D of A is the set of deformations of rho naught to the coefficient ring A, satisfying a list of conditions that we associate with the deformation type D. So we'll discuss this in great detail using Mazur's theory in chapter 8 much later. What's going to happen is for our deformation types that we're going to consider, we're going to let S first be the set of primes L not equal to P, such that rho naught is ramified at P. So I want to throw out, well, not throw it, I want to focus on primes that aren't P, where there's ramification happening in rho naught. This will always be a finite set. It's easy to show. Associated to our deformation types D, there will be another finite set of primes called a set of auxiliary primes, sigma sub D. It'll be disjoint from this S, and it will allow us to make meaningful the following definition. We'll say a deformation rho of rho naught is of type D, or of type sigma D, some people would say, if all of the following hold. First, I want rho to have p-adic cyclotomic determinant. I also want rho to be unramified outside S, P, and this new auxiliary set, sigma D. I want rho to be semi-stable outside sigma D. And if rho naught is flat at P, then I want rho to inherit that flatness at P outside of sigma D. And so what's going on here is you should think of these last three conditions in particular as saying that rho behaves a lot like rho naught does locally at primes not in sigma D. So sigma D is allowing us to throw out primes where nice conditions on rho naught, like on ramification, semi-stability, and flatness, don't lift to rho. And then, of course, I want the mod P cyclotomic determinant of rho naught to lift to the p-adic cyclotomic determinant of rho. And so sigma D is giving me a quantifiable way of lifting all the nice properties of rho naught to the deformations in consideration. So right now, you can think of deformation types loosely in terms of the set of primes sigma D associated to them. And that set allows me to lift nice properties of rho naught outside of sigma D. All right, now let's talk briefly about the universal deformation ring. Using Mazur's theory found in deformation of Galois representations, which I'll call MDG from here on out, you can show that if rho naught satisfies conditions A, B, and C above, so this is why we're imposing these conditions on rho naught, you can associate to each deformation type D what's called a universal deformation ring, R sub D. This is another coefficient ring, and it's like, it gives us the maximal type D deformation of rho naught, basically, in the following sense. It's a coefficient ring. It's unique up to unique isomorphism. It itself is equipped with a type D universal deformation rho D from GQ to GL2 RD of rho naught. Again, we'll be discussing this in chapter 8. And it has, RD has this universal property. Its universal property is as follows. The universal type D deformation rho D of rho naught has this property. If I give you a type D deformation, any type D deformation rho, from GQ to GL2 of A of rho naught to a coefficient ring with residue field K, right? There will be a unique ring homomorphism pi A from RD to A, which extends, of course, to a unique ring homomorphism GL2 RD to GL2A, just by looking at entries. That homomorphism pi A, I want it to commute this diagram, and it will commute this diagram. Okay, so what's going on here is you've got your given rho naught sitting at the bottom. Then you've got this huge, let's think of it as like a really big deformation, rho D, sitting up top to GL2 RD. And what's going on here is we're saying any other type D deformation rho that will sit nicely in between these two deformations. That's what's happening. By sits between, I mean these diagrams commute in a unique way. You see, okay? So we can cover the construction and the properties of the universal deformation ring in chapter 9. It's not particularly easy to construct. Let's look at the last condition that we want to impose on rho naught. First, a definition. Let's let G sub Q adjoin root -3 just essentially denote like the absolute Galois group of Q adjoin root -3. It's the Galois group of Q bar over Q adjoin root -3. Here's the last thing I want rho naught to satisfy. I want it to be modular, which is a big deal. This is because I want to be able to lift the modularity of it to deformations. And then there's a technical condition. I want rho naught restricted to G sub Q adjoin root -3 to be absolutely irreducible. You don't inherit that from the absolute irreducibility of just rho naught in general. So this is a technical condition on absolute irreducibility. We want a certain restricted version of rho naught to be absolutely irreducible. This will come up in chapter 7. Why put this fourth condition on rho naught? Well, under this additional condition, so if I satisfy conditions A through D, I can construct another special coefficient ring called T sub D, which will essentially be a Hecke algebra. It'll be generated by various Hecke operators. It'll be called the universal modular deformation ring. It itself will be equipped with a kind of a universal type D modular deformation, which I'll call rho DM from GQ to GL2 TD. So this is like a universal deformation, but it's also modular. And as you might expect, TD satisfies a universal property just like RD did. Given a modular type D deformation, not just any type D deformation now, but a modular one, rho from GQ to GL2 of A of rho naught to a coefficient ring A. There's a unique ring homomorphism, pi A, from TD to A, commuting the following diagram. Okay, so in other words, it's got the exact same universal property that RD had, but it only applies to modular deformations of rho naught that are type D, not just arbitrary type D deformations of rho naught. Okay, and we can even be a little bit more specific. Essentially, what's going on here is that modular deformations of type D of rho naught to coefficient rings A that commute this diagram will be modular. So one way of seeing that is you can say, okay, well, if L isn't in S union P union sigma D, in other words, it's one of the unramified primes. Okay, then the trace of rho dm of Frab L will be the Elf Hecke operator, TL, and that will allow us to see that maps from TD to A correspond to new forms. So we'll talk about that later. This will be coming up in like chapter 12, I believe. Okay. Just a little bit of insight. I mean, you might have realized this yourself. The construction of TD and rho dm is, of course, highly non-trivial, and it relies on the following deep fact, which we'll cover in chapter 7. You might think to yourself, well, how do you even know that there are actually modular deformations of rho naught in the first place? Certainly such a modular deformation and its associated ring won't exist if there aren't even any modular deformations. Well, theorem, which I'll call the ABCD theorem. Suppose rho naught satisfies conditions A through D, then there is a weight 2 new form F, such that rho F is a type D deformation of rho naught. In other words, we do have modular deformations. Okay, so starting next time, I will use this information to show you how to prove modularity in the semi-stable case. Thanks for watching.